Hey everyone, so today we'll look at Abelian group. So if you want to have a basic idea regarding the vector space, you should know about the fields, and if you want to know about the field, you should have a basic idea of what an abelian group is. So in this video we'll talk about abelian group. So basically abelian group is a set, and it is basically the set is having some sort of operation defined over it. So this dot is representing the operation. So this is just a representation. This dot can be multiplication, or can be addition, or can be a function also. Okay, like function x and y is equals to something like x square plus y square, where x and y, maybe they belong to set A. So basically this operation is a function. It can be a simple multiplication, it can be an addition, or it can be a very complicated function, but this function has to be defined on the set A. Okay, so abelian group is a set together with an operation, and it is a set together with an operation such that it should satisfy these 5 properties. So if you have some basic structure like maybe x, some sort of a structure is there, maybe x and maybe plus, this is a binary structure, and maybe you have this structure and this is the set and this is the operation, and you want to prove that this basic structure is an abelian group, then you have to prove all these 5 properties here. Okay, so here we'll look at these properties basically. So here what this closure property means. So say that 2 elements are there. Let's suppose this is the structure here, okay, and we have 2 elements. Let's say that this set is real numbers. Okay, so we'll just try it with an example. So this is the set of real numbers, and this is the addition operation that is defined. Okay, so if you want to prove that this basic structure is satisfying the property of closure, then you have to take any arbitrary elements, say x and y, from the set R, and you need to show that x plus y will also be there in R. Okay, so as we know that the sum of any 2 positive integer or the sum of 2 real numbers will be a real number. So this closure property is satisfied. So basically when the operation is applied or implemented on these 2 elements of the set, the resultant should also belong to that particular set. So this is the basically meaning of the closure property. It is closed. Basically it's like if x is a point and y is a point, and you are doing some operation, say you are just drawing a line, then it should, and this is the set of real number, then the whole line or the result of the operation should also belong to the set R. Okay, so this is the first property. Second property, associativity. This is basically as we have learned in our basic classes. So this is similar to that the operation should be associative in the set. So if we have 3 elements here, A, B, C, then they should satisfy this associative nature. Okay, and identity element. Okay, so there the third property that says that there should be an identity element in the set in order to make that particular basic structure an abelian group. So what do we mean by identity element? The identity element is an element which is operated with any element of that given set, and its resultant after the implementation of the operation, the resultant will be the element itself. So let's try on the real number. So we have, in real number we have 0, and regarding this operation, that addition, so if you take any x that is from real number and we add it with 0, the resultant will be x itself. So when we take this identity element here in the left side, it is known as left identity. When we write it like this, it is known, this will be known as right identity. Okay, so you might be having some sort of question that how will we find this identity element? So let's suppose we again take this binary structure R and this addition operation, and we want to find a binary identity element of this particular structure. Then look at the definition here, that there should exist an element E in set A such that all the elements A in capital A in set A, the equation E dot A is equals to A dot E equals to A should hold. Okay, so suppose that that our identity element is I. Okay, so what we can write I, and what is our operation here, plus, let's take any arbitrary element x should be equals to x, right, and it should be equals to x plus I. So in this way I will be equals to x minus x, right? We can write it like this, right? Okay, so what will happen if you have such kind of condition? I will equals to 0, because we know that in real number, if there is an element x and we add it with its inverse, like additive inverse here, the resultant will be 0, that is identity. So we'll find the identity like this. So I is equals to 0 here. Okay, you'll get much more clarity when we'll look the same situation with some other example. Let's see what is else there. So this is the fourth property, inverse elements. So for each element in the set A, there exists an element B in the set A such that A and operated with the other element B, and here we are taking this addition operation from our binary structure R plus. Okay, so B, it should give B plus A equals to identity, right? So in order to find, so we need to basically prove that element B is also available in set A. Okay, this is the whole thing. This is what we need to prove. So let's say A plus B, and we know the identity now, is equals to 0. That means that B is equals to minus A, and we know that in real number, if A is there in R, then there will be negative of A in R. We know by the nature of the real numbers, we know that all the positive and negative integers and fractions all are there in real numbers, rational numbers, irrational numbers. So we know that if 1 is there, then minus 1 is also there in real number, right? So we can say that additive inverse will be minus A. Okay, so it means that for any arbitrary element A, there exists minus A, that is inverse element in set A. Okay, or in set R in our case. Okay, and next is commutativity. This is basically basic, just the rearrangement thing, and if it is satisfying like this, and in a real number, we know that 2 into 3 is equals to 3 into 2, or just say that we are taking the operation addition here, 2 plus 3 will be equals to 3 plus 2. Okay, so basically it is commutative. So we can say that our example R and plus this binary structure is Abelian group. I hope that you have understood this Abelian group, and now you can solve it on your own. If you have any problem, you can just comment down and I will be replying regarding that issue.